Hey, welcome back. Today we want to look at linear models, in particular the spring models. Okay, so the picture we're dealing with is a spring attached to a ceiling or something, and then you put a little pink cube on it. You see it on the right there. Then the thing is going to stretch the spring out a little bit and it'll hit equilibrium, which is where kind of the restoring force of the spring and the force of gravity equal out. That will be one of our conditions when we go and create our differential equation to represent the system. So you'll be pulling on this spring or pushing it either physically or with a machine. If you're using a machine, they're going to have sort of a different. It'll become the non-homogeneous version of the differential equation, and it'll be like a forcing scenario. I forget what they call it. They call it a driven motion. Okay, and essentially what will happen is on the right side of our differential equation, you'll get a function that's supposed to be the driver of it. Okay. So there's going to be like three different kinds of systems. One system is called damped. So if you're like putting the spring into some sort of fluid, like maybe mud or some sort of, I don't know, lubricant or something like that, that will slow the spring down. So they'll call that damped. Okay, the original system we'll look at is free undamped, which basically means it's not driven by a machine and it's not in some weird fluid. Okay, so there'll be the free undamped, and then there's going to be free damped, and then there's going to be damped, damped driven and non-damped driven. Okay, so there's all those different kinds. You basically will solve these in the way you have before with the annihilator approach for the driven systems. And then you'll just build your auxiliary equations and characteristic equations for everything else. The driven systems, again, are going to be non-homogeneous. You'll have something on the right side. It won't be equal to 0, so you'll have to use the annihilator method to do those. But I don't think there's any variation of parameters, or you don't have to get crazy like that. You just kind of use what you learned in the section with the solving homogeneous and non-homogeneous. So it's not even going to be like the ones where you have x to the m. Okay, so that's shut up. Let's get in there and take a look at what we're up against. Okay. So first we need Hooke's law. So 5.1.1 is going to be free undamped motion. Let me make sure I'm recording. Yeah. I think I was recording. Let me look at that for a second. There we go. I can see it moving. Right. So we need Hooke's law, which you may have seen in your physics class in high school, or if you've not taken physics, here it is, Hooke's law. Basically, the restoring force is proportional to the distance that the string is stretched. And that intuitively, like a lot of physics laws, just makes sense. So if you stretch a spring out, it's going to be pulling in the opposite direction. And that's kind of what this formula is saying. In practice, you're probably going to have to solve for K. And in those cases, you're going to use the absolute value of that equation. Okay, so in practice, you'll kind of just ignore the negative part and work that way. So anyways, secondly, then let's kind of get a schematic of this system we're trying to get a differential equation for. So this is a spring mass system. Okay, so as promised, we kind of have a spring hanging from, or a cube hanging from a spring, and when the weight of the spring, so mass times gravity, is equal to the restoring force, then the object is considered to be at what they call equilibrium position. And we'll mark that off with x equals 0. If that thing goes above, and it'll be in the negative direction. So above, counterintuitively, we're going to call it the negative direction. Then if it goes below, we're going to call that going in the positive direction. Okay. So it's a little upside downish for my taste, but that's just the way the book has approached it. Different books approach it in different ways. A lot of the books I see will have the same scenario but sideways. Use Newton's law to develop the differential equation. So basically the force experienced by the object is just the sum of the forces acting on the object. So the force, again, is mass times acceleration. We'll write acceleration as the second derivative of the position function, where the position function is some function x of t. Okay. That will be equal to the restoring force, which we can write as negative k times s plus the distance away from the equilibrium position, and then plus the force of gravity. Okay. We want to simplify this, set it equal to 0, and kind of develop a homogeneous differential equation for the scenario. So first I'm going to kind of rearrange things and exploit this initial condition to simplify it. So I have m times second derivative of x with respect to t equals negative ks minus kx plus mg. Then I could rewrite that a little bit as negative kx plus mg minus ks. Okay. Because of our initial condition for equilibrium, these guys are the same. They're equal to then 0. So I can rewrite my system as mass times acceleration equals negative k times x. Then I'm going to set it equal to 0 and divide through by m. Okay, so I get d2x all over dt times m plus kx equals 0. All right, so now I'm going to divide by m. So d2x dt, there should be a little 2 on there as well. Sorry about that. How many times did I make that mistake? Okay, there. And then plus k over m times x equals 0. And then we're going to replace this k over m with a variable. In particular, you're going to call it omega squared, just so your answer kind of doesn't include square roots and all that stuff. So omega is kind of like a curly w squared, right? So ultimately then our differential equation for this kind of motion this free undamped version is going to be d2 all over x, the second derivative of x with respect to t, plus omega squared x equals 0. Okay. All right, we want to solve that and get an equation for motion. So you just go to your characteristic equation. You got your m squared plus then omega squared is 0. And we get m squared is negative omega squared. Take square root on both sides, get m equals plus or minus omega I. And so the form of our solution is in terms of cosines and sines. So I'll have C1 cosine of omega t plus C2 sine of omega t. Some of the characteristics of the motion that they'll ask for, like in the exercises, a period, you just take the omega, or 2 pi and divide it by omega. The units of that are in seconds per cycle. Frequency is just the reciprocal of that. So that will be omega over 2 pi, and that will be in cycles per second. Sometimes they'll ask for circular frequency, which is just omega. Turns out not to be a big deal for us, though, so I'm going to leave it out. There's also an alternate form for the motion equation, which is sometimes helpful, but it's kind of annoying to generate it. But I'll give it to you anyways, because I do use it in the homework, so you probably will too. So x of t is a sine of omega t plus this angle phi. Basically, what is A? A is from the constants in the general solution of the motion equation. So A is the square root of c1 squared plus c2 squared. The phi thing then is kind of annoying to get. It's sine of phi is equal to c1 all over A. Cosine of phi then is equal to c2 over A, and those two expressions will kind of tell you which quadrant you're in for that particular angle, and you can sort of retrieve the angle by using the tan formula, which is c1 over c2, and just take inverse tan on both sides, and you should be able to get it. Just got to be careful, make sure you're in the right quadrant, because the calculator won't give you an answer in the third quadrant, So, yeah. Let's get into the actual question. So there's going to be problems with units, especially in the American, fraction system, American, whatever they're calling that. For mass, that's going to end up being weight all over gravitational constant, which for us is 32 feet per second squared. And that unit is going to be slugs. Okay. For the English system, the units are just going to be newtons and meters. But for us, it's everything is, well, mass is slugs, but everything else is feet and pounds. Okay. So you're going to need that object. You're probably going to need to retrieve well, let's get in there and I'll kind of list out some of the formulas you need. What I do when I go through here is I kind of have some cheat sheets along with me where you can see here on the right, I kind of write out what I need. So this is the free undamped information. And I have it right there. I don't have to shuffle through notes every time I do a problem. Okay, so be careful about the units. Make sure you're not mixing inches and feet, and that's okay. Let's go ahead and look at maybe at a problem or two. So the first one, they're just asking for period. The second one, sure, let's try the second one. So we're going to be doing a lot of problems here. This is probably going to be a long video because there's so much to do. And I'm sure some of you probably aren't physics people, so I could be wrong, I don't know. But anyways, what they're saying is a mass weighing 24 pounds is attached to the end of a spring and it stretches it 4 inches. So, they're not saying that the mass equals 24 pounds. They're saying that the mass, if you wanted its weight, would be 24 pounds. To actually get the mass, what you're going to have to do is take that weight, 24 pounds, and divide it by 32. Okay, and that would give you your mass. So, what is that? 3/4 for mass. It's saying that once you attach it to a spring, it's going to stretch it 4 inches. So that's that force. That's Hooke's law. But we're not going to use the negative version of it. We just use kind of the absolute value version of it. The force is going to be equivalent to the weight. So you could just put 24 for force. And what you need is that K value, because your omega squared is going to be K over M. Okay, so to build our equation of motion, I need omega. And so I'll need to retrieve the K value from this force equation in this example. anyways, be careful. They're saying it stretches at 4 inches, but you have to convert that to feet. So it's going to be 4/12 of an inch. In other words, 1/3 foot. Then you can multiply both sides by 3. You get K equals, okay, 12, carry the 1, 6, 72. All right. What else did it tell me? Initially, the mass is released from rest 6 inches below the equilibrium position. So x of 0, the original position, 6 inches below is positive 6/12 of a foot, so that'll be 1/2 feet. It's released from rest, so the velocity is what they're telling you there, x prime. That will be 0. And then I think we have probably enough information to get the equation that we want. So rather than working with the differential equation, I'm just going to get the equation of motion and put in omega. So omega is, again, omega squared is k over m. So k is 72, m is 3/4. So that will be 72 times 4/3. 3 goes into 72. 2 times, so this will be 48, apparently. That don't seem right. So I could have made a mistake. Let me pause the video and check my work, make sure it's all right. Oh, I see. I don't know what I'm thinking sometimes. It's early for me. I just got up. That's my excuse. So 3 goes to the 7 times 2 times, and then 1 comes down, 2 comes down, so that would be 4, 24. Sorry, guys. This will be the first of many mistakes this morning. 24 times 4, 16, carry the 1, it's 96. That sounds better. Right, so my equation of motion, I'm going to need omega, so the square root of 96 basically, which will be, so 96 divided by 16, that will be 3. Goes into it, no, 6 times. So 6 times 6 is 6, carry the 3. Yeah, that'll work. Okay, so omega will be 4 square root 6. So my equation of motion, C1 cosine of 4 root 6t plus C2 sine of 4 root 6t. You're not done. Now you need to go back to your initial conditions and solve for the constants. Okay. So plugging in x of 0 is 1/2. I got 1/2 equals C1 times cosine of 0 will be 1. Cosine of 0 is 1. It's really 0 times 4 root 6, but 0 times 4 root 6 is 0. So cosine of 0 is 1. Sine of 0 is just 0, so you get C1 is 1/2. Then I'm going to plug in, get the derivative and plug in the second initial condition. So x prime is going to be negative 4 root 6 C1 sine of 4 root 6t. And then the other guy plus 4 root 6 C2 cosine of 4 root 6t. Plug in that other initial condition, 0, 0, so 0 equals, the first term will just be 0 because sine of 0 is 0. The second term will be 4 root 6 C2 times 1. Solving for C2, you see that's 0. Okay. Plug those initial values into your, plug those constants now into your motion equations. So you get C1, which is 1/2, cosine of 4 root 6 t, and then plus 0. And you can see that's the answer over in there. Little bit of trig stuff going on in some of these questions. Like you see part C, that answer probably may look a little funny to you. Let's see if we can kind of cruise through that problem and see why I have that funny answer there. So number 3, mass weighing 20 pounds stretches a spring 6 inches. So the actual value for mass in slugs is going to be the weight 20 all over 32, the gravitational constant. Divide top and bottom by 4, you're going to get 5/8 for the mass, 5/8 slugs. Then I need the constant k, right? Because omega squared, again, is going to be k over m. So the k value, again, you retrieve it from the Hooke's law. and I'm going to plug in 20 for force. That will be the weight of the mass, and then K times not 6 but 6/12, right? So that'd be 1/2 of a foot. Solve for K. K must be 40. So omega squared is going to be 40 all over 5 over 8 multiplied by reciprocal. So 8 over 5. 5 is in the 48 times, so it looks like it's going to be 64. So omega is just going to be 8. And for our equation of motion, then x equals c1 cosine of 8t plus c2 sine of 8t. All right, part A, they want you to find the position of the mass at these given times. So all you're doing there is plugging in their values. So let's do one of them. I'll leave the rest to you. X over pi, x of pi over 12, sorry, is going to be c1 cosine of 8 pi over 12. 8 pi over 12 is the same as 2 pi over 3. And then, whoops, I didn't get my constants. Sorry, I'm going to have to get my constants before I can do this, right? So I'm going to need the initial conditions. It says the mass is initially released from rest at a point 8 inches below equilibrium. So original position is 8 inches, so 8/12 of a foot. So that'd be 2/3 of a foot. And then its initial velocity, because it's released from rest, is going to be 0. And then I can get my C1 and C2, right? So plugging in this into here, I get 2/3 equals C1 cosine of 8 times 0. That would be cosine of 0. Cosine of 0 is 1, so I get C1. Sine of 8 times 0 is the sine of 0. Sine of 0 is 0, so the rest is 0. Get the derivative. So I have negative 8 C1 sine of 8t plus 8 C2 cosine of 8t, and then plug in the other initial values. So I get 0 equals 0, because sine of 0 is 0, and then 8 C2 times 1. So again, looks like our equation of motion is just one trig function, in particular 2/3 cosine of 8t. Okay. All right, so now let's go to part A. We have x of pi over 12, so that'll be 2/3 cosine of 8 pi over 12, which would be 2 pi over 3. Where is 2 pi over 3? So it's 1 pi over 3, 2 pi over 3. It's in the second quadrant. Reference angle is 1/2. So I'll have 2/3 times negative 1/2, because it's in the second quadrant, and cosine is negative in the second quadrant. So you'd end up with negative 1/3 feet. Then part B, they want the velocity questions. So I go back to my equation of motion and get its derivative. So x prime is going to be negative 16 thirds sine of 8t. So the velocity at 3 pi over 16 is going to be negative 16 thirds sine of 8 times 3 pi over 16 will be 3 pi over 2. On the unit circle, 3 pi over 2 is down here. Sine is negative 1 there, so it's going to be negative 16 thirds times negative 1, which would be positive 16 thirds. That's a follow-up question. Is it going down or up? Remember, upwards is negative, so it's going down. Part C, when does the mass go through the equilibrium position? So now you need to work with the position function and basically just set it equal to 0. Okay, so you have like a trigonometric equation. Whenever you have those scenarios, you're going to get like 2n pi. You have this n to represent integers, because there's going to be an infinite number of times in this kind of unrealistic setting where the weight is free and undamped. It's just going to keep going up and down and up and down. So anyways, solving this thing, you're just going to get cosine of 8t is 0. So you're looking for when 8t is going to be equal to an angle that makes cosine 0, right? Cosine is 0 at pi over 2, and then odd plus odd multiples of pi. So it's 0 here, and then here, and then here, and then here, okay? So it's going to be plus some multiple of pi, and you just use n for the multiple, and then divide everything by 8, and you get pi over 16 plus pi n over 8. And that turns out to be the answer that you see that I wrote in, but I just made it look nicer. Okay. All right, great. Let's look at another one. So, maybe this number 5 would be kind of weird because you're not used to writing out those infinite solutions to trig functions. So let's try it, right? This time they're telling you the mass is 1 slug, so m is just 1. And then they're also telling you the spring constant, so k is 9. Mass is initially released from a point 1 foot above equilibrium, so x of 0 is going to be -1. And then it's saying it's released with an upward velocity of √3. So because it's going upwards, it's going to be a negative √3. Find the time when the mass is headed downwards at a velocity of 3 feet per second. So I'm going to have to produce a velocity equation like I did here in part C. Well, actually, it's more like part B. I got to get the derivative of the position function and then set it equal to, in this case, 3. Okay, because they want to know when the object is moving downwards at 3 feet per second. Okay, so let's create that equation then. So in our case, omega squared is going to be just 9. So we can get our equation of motion from that. It's going to be C1 cosine of 9t plus C2 sine of 9t. Use the initial conditions. So x of 0 is -1, so -1 equals C1. Cosine of 0 is just 1. Sine of 0 is 0, so it's just C1 is -1. Get the derivative. So I have -9 C1 sine 9t plus 9 C2 cosine 9t. And then I want to put in the other initial value, so -√3 equals, the first term will be 0, the second term will be 9c2. Okay, so did I take the square root? Oh, whoops, sorry. So I got the constant wrong there. So omega is 3. There's so many places you can make little mistakes, it's not even funny. So this should be 3. Sorry about that. Okay, so here, then these should also be 3s from the chain rule. So here, this would be a 3, and we would get C2 equals -√3 over 3, I believe. Okay, so assuming I didn't make any mistakes. Anyways, we can then rebuild our equation of motion. Actually, though, what we need is that derivative for the velocity, right? So I'm just going to work with that. Plugging C1 and C2, first I get 3 sine 3t, and then minus 3 times √3 over 3 is just going to give me a √3 cosine of 3t. And then I need to set this thing equal to what? Equal to the, so find the times for which the mass is headed downwards at a velocity of 3 feet per second. Okay, so I need to set this thing equal to 3 apparently. Yeah, and this is trouble, right? Because the big problem is solving this equation is not an easy task. So this is where the alternate form of the motion equation comes into play. If I had it in this form, it would be a lot easier to work with because I could just take inverse sine on both sides or something like that. So that's what I'm going to do. I'm gonna rather than work with that form, I'm going to just convert the motion equation into the alternate form. Okay. Okay. So what do I need to do that? Let me pop out my cheat sheet here. I need this a value, and a is going to be the square root of c1 squared, which is 1, plus c2 squared, which will be 3 over 9, which is 1/3. Then that's going to be square root of 3/3 plus 1/3 is 4/3. So that's going to be 2 over root 3. And then I need to figure out this phi value, that angle you see on the right, and a sine of omega t plus phi. So first I got to kind of acknowledge what quadrant I'm in. Sine of phi is going to be c1 over a. A is always positive. C1 tells you the sine of phi. Okay, C1 is negative, so sine of phi is negative. Then cosine of phi, C2, then if you look at that value is negative, so cosine of phi is going to be a negative over a positive, which also is negative. And what does that tell me? It tells me I'm in the third quadrant, because both sine and cosine are negative. Okay, so I can go to my tan formula and solve that, but I have to be, I have to acknowledge that the angle I need is in the third quadrant. So anyways, tan of phi will equal C1, which is 1 all over C2, which is or negative 1 all over C2, which is negative root 3 over 3. Taking reciprocals, you'll get 3 over root 3, which is just root 3. Okay. Then I even, that's a reference angle for tan, right? So what angle gives me root 3 in the first quadrant? So the reference angle would be, I guess that would be pi over 3. We need the particular phi that's in the third quadrant. So 1 pi over 3, 2 pi over 3, 3 pi over 3, we need 4 pi over 3. Okay. And then we could form our alternate form of the equation of motion. So that's going to be x of t equaling a, which is 2 over root 3, times sine of omega, which is 3t, plus this phi value for pi over 3. And then I'll get the derivative and set it equal to 3. And I should be able to solve it easily. Okay. Times, I guess, 3 cosine of 3t plus 4 pi over 3. Clean it up a little bit. Prime of t is going to be, I guess, 2 root 3. Is that right? The heck was a again? Yeah, a is 2 over root 3. And then when I took its derivative, the chain rule would give me a 3 in there. So it's going to be 6 all over root 3 cosine of 3t plus 4 pi over 3. And we need to set that equal to 3 to find when the velocity is 3. So I have this thing. Multiply both sides by root 3 over 6, you get root 3 over 2. So cosine of 3t plus 4 pi over 3 is going to be root 3 over 2. Now you have another trigonometric equation, so you're looking for all angles that make cosine equal to root 3 over 2, right? And there's 2 of them in the interval from 0 to 2 pi, and we use those kind of as the generators for all the other angles. So the first angle where that will be true is in the first quadrant, and that will just be pi over 6. And then the second angle where that's true, that's the fourth quadrant, which is 11 pi over 6. Okay. So we'll have 2 kind of generating equations that are going to be formed. 3t plus 4 pi over 3 equals pi over 6 plus 2 pi n. And then 3t plus 4 pi over 3 equals 11 pi over 6 plus 2 pi n. Okay. And then you just solve for t. So 3t will be 4 pi over 3 is the same as 8 pi over 6. So you're going to end up with negative 2 pi over 6 when you move that over. Is that right? 4 pi over 3 is 8 pi over 6. Yeah. So you're going to end up with rather negative 7 pi over 6. There we go. That sounds better. Plus 2 pi n. Divide both sides by 3. You get t is negative 7 pi over 18 plus 2 pi n over 3. So that's one set of solutions. The other set, you get 3t equals 4 pi over 6 is the same, again, as 8 pi over 6. Moving that over, 8, 9, 10, you get 3 pi over 6, which is pi over 2, plus 2 pi n. Divide everything by 3, so you get pi over 6 plus 2 pi n over 3. Okay? And that should be the answer I put in there. Yeah. Number 6 was kind of weird for me for some reason. They replaced, they have this kind of factor in there, this e to the negative 0.1 t x that you can kind of see. So it's 4 times the second derivative of x plus e to the negative 0.1 t times x equals 0. It's saying that for large values of t, you can approximate the differential equation with x double prime equals 0. So if you think about that differential equation, x double prime is 0, and get the auxiliary equation, or what I sometimes call the characteristic equation, m squared is 0. The roots there are 0 and 0, so your general solution for that equation of motion, assuming that one term is 0, is going to be c1 plus c2 t, right? And that's what they want in that first answer. And what does that mean with regards to the spring? So basically, as time goes on, the value for x is just going to get bigger and bigger and bigger, right? So if x is in the downward direction, positive in the downward direction, that means the spring is just stretching out and out and out and out and out and out this way. Okay. So over the long time, it's never going to go back, right? So the restoring force is going away, and basically that means it's decaying. And so in the long run, it's going to just keep on stretching and probably break, right? So that's kind of what they're going after there in that picture. The next picture is kind of going towards this idea of damped motion. There's 3 kinds of damped motion. There's critically damped, overdamped, and underdamped. When something's overdamped, it's like you're putting the spring system into mud, right? So it's not going to oscillate up and down. It's probably going to slow down significantly and then just go back towards its resting position. And that's what this graph is kind of suggesting, okay? So initially, the value is negative, so that the little weight is above equilibrium, and then it's just slowing, it goes even more above, and then it slows down, and it just comes to rest at the equilibrium position. And that's generally what happens when you have overdamping. If it's in this really, really, really slowing liquid or substance like glue, it's going to be slowing down, and it's never really going to be oscillating like a normal spring would. Just be careful again with the orientation. For negative values, that means the spring is located above equilibrium. And if it's headed above, if it's going upwards, that means it has positive, if it's headed upwards, it has negative values, okay? And you can see in the graph on the right here, it has negative values, so it's in the upward position. In the beginning, it's going even farther upward, okay? So when the mass is initially released from rest, it is actually going upwards. It looks like it's going down, but it's going up because everything's upside down, right? So yeah, damped motion is the second kind of motion we want to look at. It's still free motion. In other words, there's not like a motor attached to the thing and it's going back and forth like a piston or something. But 5.1.2 is going to be a spring with free damped motion. Okay, so again, the picture that you're thinking of here is going to be the spring is inside some sort of fluid like glue or maybe even, I don't know what they put, Vaseline or whatever, you know. Okay, so what we're going to do in these cases is just kind of augment the original differential equation for motion that we have for free undamped with an additional term which represents damping. Okay, and the damping will be proportional to the velocity, just kind of like wind resistance, right? The faster you go, the more resistance you're going to feel. So, right. So let's get the differential equation for this scenario. And again, the big change is going to be an extra constant. We always begin with this m on the other side. And you'll see that when we develop the formulas for driven motion, you're going to have to divide by this m, and it'll affect the right side of the non-homogeneous differential equation. So, but anyways, here we go. So normally it would just be negative kx, but then we're going to subtract away this damping constant, which will slow the motion, right? So negative beta times the velocity, dx over dt. And that would be the damping force. So when they describe it in the exercises, they'll say something like the damping force is numerically equivalent to 10 times the instantaneous velocity. But what they're telling you there is the beta value. They're saying beta is 10. Let's look at this question. The damping force is numerically equivalent to 1.6 times the instantaneous velocity. Again, 1.6 is going to be the beta value in that scenario. Anyways, let's take this differential equation and take a look at the solving process. So first, again, we want to put it into the form where it's set equal to 0, and we're going to divide everything by m. Okay, so first, set it equal to 0. And kind of put it into our linear differential equation form. Okay, divide by m. And then we're gonna, again, replace k over m with omega squared. But we're also going to let beta over m be replaced with the 2 lambda. Okay? So let 2 lambda equal beta over m. And those will be the kind of the 2 bits of information we need to get us started whenever we go to these differential equations. Let me rewrite it in all of its glory. So there's our differential equation. The auxiliary equation, or whatever it's called, the characteristic equation, let's get that so we can see what happens when we're trying to solve this thing. Again, there's going to be kind of like the 3 cases, the repeated root case, the distinct root case, and the imaginary root case. It'll all come down to the discriminant. So in particular, we want to kind of look at the discriminant in these cases. So again, the auxiliary equation in roots will have m squared plus 2 lambda m plus omega squared is 0. And so we'll have m equals negative 2 lambda negative b plus or minus the square root of b squared, which is 4 lambda squared, minus 4 times a, which is 1, times c, which is omega squared. And that'll be all over 2 times a. So I want to simplify this. Negative 2 lambda plus or minus, I can factor the 4 out, and then the square root of 4 is just 2. It's the square root of lambda squared minus omega squared. It's all over 2. Simplifying, I'm going to get negative lambda plus or minus square root of lambda squared minus omega squared. And so what's going to happen is we look in at this discriminant, and that kind of tells us what kind of case we have. And again, there's three cases. There's the overdamped, the critically damped, and then there's the underdamped. Okay. So the overdamped is the case when the discriminant is greater than 0. So you have two solutions, and they're both going to be exponential decay solutions. So over time, you would expect that the motion is going to be 0. So when this is greater than 0, it's overdamped. Critically damped is kind of in between underdamped and overdamped. That's just when these equal 0. And the behavior is very similar to what you see with the overdamped case. The underdamped is when you have imaginary solutions. So again, when you form your general solution, you'll have some trig equations or trig expressions in it, so you'll have oscillation. It'll be going up and down and up and down. Okay, so those are your three cases. Yeah. Well, let's look at some of these problems then with regards to underdamped, overdamped stuff. Number 12 kind of introduces you, I think, in a good way. So a mass weighing 14 pounds stretches a string 2 feet. So again, we still have to go and retrieve all of this information. We need our, what do we need? Omega squared, which is going to be k over m. We need our 2 lambda now, which is going to be beta over m. To get k and m, I need to work with the weight. So the weight to get the value for m is 14. You put that over 32 for the gravitational constant. Excuse me, that's going to be 7 all over 16, I believe. Oh my god. And then I'm going to get omega squared. I need the constant k. So I need to use my Hooke's law formula for that. So 14 equals k times 2. So k is apparently 28. And then I can get k over m. So k over m in this case, our omega squared, is going to be 28 all over 7 all over 16. So that's going to be 28 times 16 over 7. 7 goes in the 28 4 times. That will be 64. So omega is 8. Then for 2 lambda, I need the beta value. And it's saying that the damping force is numerically equal to beta times the instantaneous velocity. That means they're not giving you the beta value. Okay, so anyways, where was I? So you're not really told the beta, right? So 2 lambda then is going to be just regular old beta all over the m value, which we found to be 7/16. So you can rewrite this as 16 beta over 7 if you want. All right. What are we doing? Determine the values of the damping constant so that the subsequent motion is overdamped, critically damped, or underdamped. Okay, these things. So we need, what do we need? We need lambda squared minus omega squared. So lambda here, dividing both sides by 2, is going to be 8 beta all over 7. Okay. And then we can square it. So we get lambda squared is 64 beta squared all over 49. And then look at what these values are, lambda squared minus beta squared. So lambda squared minus beta minus omega squared. Lambda squared minus omega squared is going to equal 64 beta squared all over 49 minus 64. What you want to do is kind of set that equal to 0 so you can find where it's critically damped. And that will cut your basically set of values into two intervals. Okay, so setting this thing equal to 0, I'm going to multiply everything by 49. So I get 64 beta squared minus 64 times 49 equals 0. And then I can move the 64 times 49 to the other side. Oh, crud. Yeah. And then, hold on. Sorry, I see my mistake. It's back here. So this should be, the k value should be 7. Sorry. So I'll screw some stuff up. That would make omega squared here is kind of screwed up. So this is going to be 7. Reciprocals, I'll just have to make 16. And so this guy is going to be 16 here. And then I'm going to multiply through by 49. And this will be 16, 16, 16. So beta will be 16 times 49 all over 64. So that'll be 49 all over whatever that is, 4. And then 4 goes into 49, 1, 9, 2, 0.2, 5. Okay, so beta is going to be 12.25. And that's where the thing is, well, beta squared is that, right? So that'd be beta squared. So beta is actually square root of 12.25. And that becomes where it's critically damped. Anything below that, but greater than 0, will be underdamped. So this is critically damped. For underdamped, where you actually have oscillation, that will go from 0 to the square root of 12.25. And then for overdamped, that will go from square root 12.25 to infinity. Okay. So I don't think they made it clear. If you're just ripping through these questions, that you have to use interval notation for some of these. That's why I kind of wanted to do that one. Anyways, let's look at some of these other guys. Seems like this one is kind of weird. Number 11. So let's take a look at that guy. Force of 13 pounds, stretches a spring 1 foot. Okay, so get my weight, or sorry, get my mass for my weight. So mass is going to be 13 all over 32, unfortunately. For the K value, force, which is 13, will equal K times S. In this case, S is just 1, so K is 13. I need my omega squared. Omega squared, of course, is your K over M. So that will equal 13 all over 13 divided by 32. Taking reciprocals, that should just be 32. 2 lambda, you're going to need beta. Okay, so 2 lambda, it says the damping force is numerically equivalent to 1.6 times the instantaneous velocity. So you have 1.6 for beta, and then divided by m, which is 13 all over 32. One minor detail on the previous question, previous question, it says the medium offers a damping force that is numerically equivalent to the instantaneous velocity. That just means beta is equal to 1. Okay. Usually they'll say it's 10 times the instantaneous velocity, for example. But if they just say the medium offers a damping force that's numerically equal, that means beta is equal to 1 times the instantaneous velocity. Beta is 1. Okay, long story short. Okay. Anyways, let's look at this guy, right? We have then 1.6 times 32 all over 13, whatever the heck that is, right? 1.6 times 32 divided by 13. It's nothing nice. How about just, I mean, really? You're going to do that, you know? What is just, I mean, really? Okay, I see what I did. The force of, so if you applied a force to the mass of 13 pounds, it'll stretch the spring 1 foot. The mass actually weighs 6.4 pounds. Okay, so, all right, very clever, right? So I need to change this into 6.4. And then I'm going to rewrite this thing, what is it, 64 all over 320. So that'll be 32 times 2 all over 32 times 10, which is 1/5. Okay, so m is actually 1/5. Again, I apologize. So I get 1/5 here, 1/5 here. And then this guy will be 565 for omega squared. 2 lambda then is beta, so 1.6 all over m, which we just figured out was 1/5. So, 1.6 times 5, 6 times 5 is 8. So I have 8 for 2 lambda. Now I'm going to form my auxiliary equation. So it's going to be m squared plus 2 lambda m plus omega squared equals 0. So that's going to be, can I even factor that? It don't look like it, right? So I got to go to the quadratic. -8 plus or minus the square root of b squared, 64. Minus 4 times a times c, which is just 1 times 65, all over 2. 64, let's just go 4 times 65 minus 64, and then take the square root of that. That's 14, but it will be negative, so it's a 14i. So -8 plus or minus 14i all over 2. And then I can simplify that to -4 plus or minus 7i. So my solutions give me sort of the underdamped version. It'll be e to the -4t times c1 cosine of 7t plus c2 sine of 7t. I'm tasked with finding the equation of motion in part A if the mass is released from rest at a point 1 foot above equilibrium. So x of 0 is 1 foot above, that means it's negative, and then x prime of 0, it's at rest initially, so just 0. I need to get the derivative of that ugly thing. Okay, so it's going to have 4 terms to it because of the product rule. So anyways, let's go ahead and get the derivative. I'm going to need it anyways. So x prime of t, I'll take the derivative of e to the -4t first. So -4e to the -4t times c1 cosine 7t plus c2 sine 7t. And then I'll leave the e to the -4t alone, and I'll have -7 c1 sine 7t plus 7 c2 cosine of 7t for the derivative. Okay. Plugging in the first initial condition into the motion equation, I'm going to get -1 equals e to the 0, which is 1, times c1 cosine of 0. Cosine of 0 is 1, so just c1. Sine of 0 is 0, so c2 times 0, that's just 0. Now I'll take the second initial condition and plug it into the derivative. So I have then the second part, 0 equals -4e to the 0, so -4. times C1 cosine of 0. Cosine of 0 again is 1, so I have C1. The C2 bit is 0, because sine of 0 is 0. Plus e to the 0 again is 1 times negative 7c1 sine of 0 is 0, so that first part is 0. And then 7c2 cosine of 0 is just going to give me plus 7c2. All right, so I can solve for c2. 7c2 equals 4c1. And so c2 must equal 4/7 c1. C1 is negative 1, so C2 must be negative 4/3. And then I can build my equation of motion for this case. X of t is e to the negative 4t times negative cosine 7t minus 4/3 sine of 7t, which is what you see. I put it in part A. Part B, they have like an alternative form for the alternative equation of motion when you're dealing with an exponential value in your answer. So in this case, their alternative form is ae to the negative omega or negative lambda t. So negative lambda t, and then sine of the square root of, just lost it, where the heck are you? Omega squared minus lambda squared, and then the t is on the outside of that. You can't tell when you read it, but the t is on the outside of it, and then plus, whoops, I forgot my angle phi, plus phi. Alrighty then, so I need the a value. The a is just like the a that we found before. It's c1 squared plus c2 squared. c1 is 1, negative 1, but squaring it is 1, and then plus 16/9. So you get 9/9 plus 16/9 is the square root of 25/9, which apparently is 5/3. No, that's not right. What the heck is lambda? 2 lambda is 8, so lambda must be 4. Oh wait, no, I'm right. This is the a value. So it's 1 plus the 16/9. 9/9 plus 16/9 is 25/9. It's 5/3. And for some reason, I'm not getting that for my answer. Does it say what a should be? Well, they give you a formula here. I don't know where the heck it is. It's in the book somewhere. Scroll down and find it. Here it is. Yeah, a is c1 squared plus c2 squared. Pause the video again. Oh, I see it. It's not 4/3, it's 4/7. Oh my gosh. 4/7 right there. So then this guy will be a 7. And then this will be 16/49, and then that screws it up, right? So this would be 49/49 plus 16/49, adding 16, 5, 1, 4, 5, 65 49, so the square root of 65 over 7. Okay, sorry about that. What else do I need? Lambda, I just said was 4. So lambda squared must be 16. Yeah. So lambda squared must be 16. Omega squared we already had up there is 65. So the square root of omega squared minus lambda squared is what I'm kind of after. Square root of 65 minus 16. Which is really square root of 49, so it's 7. Then I need that angle phi. So again, you kind of have to work with cosine and sine. Note C1 and C2 are both negative, so it's going to force sine of phi to be negative and cosine of phi to be negative. In other words, again, we're in the third quadrant. And then I just take tan of phi and set it equal to -1 all over -4/7. So that will equal 7/4. Sadly, I have to go to my calculator for that. So phi from my calculator, and I'm in radians. If I can find my calculator, that would be nifty. Alright, so clear tan inverse of 7/4. Of course, my calculator's dying. So we may not be able to do this really. Every time I hit the enter button, my calculator dies. Dies a little inside, so I'm gonna have to go to Wolfram. Wolframize it. Alright, so arc tan of 7/4 is about 1.0516. The problem with that angle is that it's in the first quadrant, and we want our answer to be in the third quadrant. It's an easy fix. All you have to do is add pi to it. So our phi will be pi plus this computer answer, so 4 or something. So plus pi is 4.19. And I think the book just wants 2 decimals. 4.193. Okay, so we're good. You can put all this together then, and you have your little formula that is so important for them to get you to get. That's equal to square root 65 all over 7, e to the -4t times, what is it, sine or is it cosine? I think it's sine. Sine of omega square root of omega squared minus lambda squared is 7, and then plus this 4.19 angle in radians. So you see that there for the answer. Find the first time the mass passes through equilibrium headed upward. Okay, so initially note that the thing is headed, so it's released from a point 1 foot above equilibrium. So first it's going to go downwards through the equilibrium point, and then you'll get like a false answer there, but then it goes back up. So you need the second time it goes through the equilibrium for the answer. So what you got to do is set this equation equal to 0. So 0 equals square root 65/7 e to the -4t sine of 7t plus 4.19. You can divide out by all this mess and just get sine of 7, because that stuff's never going to be 0, plus 4.19 equals 0. Then you're looking for angles that cause sine to be equal to 0. So you have 7t plus 4.19 equaling 0 plus pi n, right? 0 plus pi n. So you get 7t equals -4.19 plus multiples of pi, divide both sides by 7, all over 7. So clearly when n is 1, that doesn't even make sense, because that's going to give you a negative time. When n is 2, that will be the first time it goes through the equilibrium point. So we want to let n equal 3. That'll be going back up through the equilibrium point. So t in that case will be -4.19 plus 3 pi over 7. And then you go to your computer or calculator. My calculator set is always dying. My calculator is just always dying. -4.19 plus 3 pi, all that divided by 7 is 0.748-ish. I don't know how many decimals they wanted, but you can see that's the answer. Okay. All right. Right. So that's the damping stuff. The next sort of group of exercises, I think there's only 1 or 2 actually that I put in the homework. The next group are based off of driven equations, which are basically just the damped or the undamped with a function on the right side. Instead of having them equal 0, like we have had in our differential equation. So here you see that the damped free motion is equal to 0. Originally, the undamped free motion is also equal to 0. If to model driven motion, you're going to put a function on that right side, so an f of x. What's really dangerous is that you have to remember to divide f of x by the mass. If you don't, you could be in trouble. Okay, so anyways, this is like the 3rd section. This will be the last section I really deal with. Driven motion, both damped and undamped. The differential equation, as promised, then the differential equation for this scenario will just be your regular differential equation, but then with a forcing function on the right side. So plus, if it's the damping version, plus 2 lambda dx over dt plus the omega squared. So this is the damped driven omega squared. But there's really not too much of a difference when you go in to solve them. And it'll equal the forcing function, but you have to remember to divide that by the mass. Okay, the book overall calls that big F of t. So what you see is just you have the same kind of equation as before, but now you have it being non-homogeneous, so you'll have to use the annihilator method to solve these. Okay. Okay, so there's the damped driven and undamped driven. They talk a little bit about the undamped driven with regards to resonance, which is really, really fascinating. I just don't have time to go through it towards the end here, I think. Okay, so driven motion without damping, what they do is produce kind of a motion equation, just abstractly, and then they talk about pure resonance. If you look at the equation for motion in this case, it has that denominator omega squared minus lambda squared. So basically when those two constants approach each other, you'll have like an L over 0 form, which will, as time goes on, it'll go to infinity. Okay, so your motion just goes, what that means is the motion will go out of control, like in this picture here where you see pure resonance. And it causes bad things to happen if that's your machine. You know, the machine will blow apart, basically, if your machine goes in the pure resonance. Anyways, it's really interesting. I advise you to read it, but I'm not going to go through it. I just want to hit the last 2 kind of exercises so you can get through the homework. Number 13, we're given that the mass of 1 slug, so the mass is 1. When it's attached to a spring, it stretches at 2 feet. So I need to retrieve the weight from the mass. So the mass is the weight all over the constant. So it must be 32 for the weight. So I'll say 32 is the force equals K times the amount it's stretched, which is 2. So it looks like K is going to be your 16. Then your omega squared, K over M, which is just going to be 16. You need your 2 lambda, which is beta over M, which in this case, beta the damping force is numerically equivalent to 8 times the instantaneous velocity. So 2 lambda is 8. What else do we need? They're giving us an little f of t, which is 10 sine of 4t. Usually it'll change when you divide it by m for big F of t, but in this case it doesn't, right? Because m is equal to 1. So you just get 10 sine of 4t here. So you could screw that up, but then when you get to the next problem, it's not going to work. You just put in 10 sine 4t, because you got to divide it by mass, and mass is not 1. Anyways, I think we have enough to kind of get our, we probably have some initial conditions, unfortunately. Starting at t equals 0, okay, blah, blah, blah. It's in equilibrium position and it's not moving. So I believe the initial conditions to be x of 0 is 0 for equilibrium and x prime of 0 is 0 for not moving. Even if you want to argue that the motion is dictated by the function, like as soon as you turn it on, it'll be in motion. I guess you're not going to think of it that way. It's just instantaneously at that beginning, it's not moving. Okay. So anyways, let's set up our differential equation. We don't even have to bother, right? Let's just go to the characteristic equation. In that case, it'll be m squared plus 2 lambda m, so 8m, and then plus omega squared, which is 16. You want to solve the homogeneous version and then go to the non-homogeneous. So the non-homogeneous version, this would be equal to 10 sine 4t. Okay, so we'll use the annihilator method again to pull that off. All right, so anyways, the associated homogeneous version, the auxiliary equation is that. So the roots looks like it's going to be -4 and -4. So the complementary part of the solution is going to be c1 e to the -4t plus c2 e to the t e to the -4t. Don't let me screw up like that again. Okay. T e to the -4t. And then I work over to my non-homogeneous version and build my annihilator. So the part I already have, the d plus 4 squared, to annihilate the 10 sine of 4t, that's going to require an imaginary roots, m equaling, I guess, plus or minus 4i. Okay. So the annihilator for that is going to be d squared plus 16. And then apply that to the non-homogeneous equation there. That will equal 0. And so engineer the solutions of this differential equation, and you get roots plus minus 4i, and then plus minus, minus 4, right? So -4 and repeated -4. So in that case, our general solution be, let's just write c1 e to the -4t first plus c2 t e to the -4t, and then the rest of it would be plus c3 cosine 4t plus c4 sine 4t, right? So the particular part of the solution would be all this junk. That's our x of p. So let's work with x of p. So x of p, we'll replace the constant with a and b. A cosine 4t plus b sine 4t. And then I could take derivatives of that thing. So I get xp prime is -4a sine 4t plus 4b cosine 4t. X double prime p is going to then be -16a cosine 4t plus minus 16b sine 4t. Okay. Then we want to plot that all back into our original differential equation back here. go at it, right? So I'm going to need, and sometimes I cheat a little bit, so I just kind of do it in-house. So I need, 16 of these. So there will be 16a cosine 4t plus 16b sine 4t. Then I need 8 of the x primes, because the original differential equation, I know I didn't really write it, but from this auxiliary form, you can kind of see what it is. Right? It's just that thing. Anyways, then I could sort of just add up like this, add them all together, and then set it equal to 10 sine 4t. So 16a, negative 16a cosine 4t will add away with that. Negative 16b sine 4t will add away with that. And then, did I multiply this by 8 yet? No, I didn't. So it's 8 times this junk, which will be negative 32a sine 4t plus 32b cosine 4t, and that equals 10 sine 4t. Then we equate coefficients, so negative 32a equals 10, and then the 32b is just 0. There's no cosine 4t on the right. Divide both sides. A is then negative 5/16, and then b is 0. So then we can form our solution to the differential equation. X is going to be equal to C1e to the negative 4t plus C2t e to the negative 4t, and then the particular part minus 5/16 sine 4t. Okay, and hope that's right. Yeah. I still need to get the constants C1 and C2 from the initial conditions. So I just remind myself the initial conditions: x is 0 is 0, x prime of 0 is 0. Plugging in the first initial condition, and I get 0 equals C1 e to the 0 is C1 times 1, so C1, plus C2 times 0 times e to the 0 is just 0, minus 5/16 sine of 0 is also 0. Okay. Then I get I need the derivative here, so x prime is going to be negative 4 C1 e to the negative 4t. I need a product rule on the next one. First taking the derivative of t, I get C2 e to the negative 4t, and then taking the derivative of e to the negative 4t, I'll get minus 4 C2t e to the negative 4t, and then finally this will be minus 5/4 cosine of 4t. Okay. Can I combine anything there? Not really. Substitute in the initial condition again. So 0 is negative 4 C1 e to the 0 is 1, plus C2 e to the 0 is 1, minus 4 times C2 times 0 times 1 is just 0, and then minus 5/4 cosine of 0 is 1, so minus 5/4 times 1. So C1 is already 0, so C2 must be equal to 5/4. And finally, I'll have my equation of motion. So x is C1, which is 0, plus C2, which is 5/4 t e to the negative 4t, and then minus 5/16 sine of 4t. It seems like I have a mistake in there. But, you know, no, I guess I do. It's that first one. Let's see where it was initially let go. String at t equals 0, or some, so it stretches at 2 feet, and then it's at rest in equilibrium, so it's x of 0 is 0. Did I miss something? You know? So let me pause and look for it. Okay, I see the issue. The A is actually with the cosine, so it's not sine here, it's actually cosine. That'll change things. Sorry about that. So this is actually then cosine of t, and then this will change this. So this would be x, or rather 0, when you plug in 0, equals c1, e to the 0 is just 1, minus 5/16. So that tells me c1 is 5/16. And then for the next guy, this last term will be a sine term. Okay, so it's the derivative of negative 5/16 cosine. And it should be, is it 4t? Yeah, there should be a 4 in there. So chain rule times 4, that's fine then, sine 4t. But it was a cosine first, so it'll become positive from the derivative. And then this will be plus. And then I'll have to erase this junk. So I have, what? 0 equals negative 4 times 5/16 plus C2 plus 5/4 is the same as 20/16. Now I'm getting C2 equals 0. Okay. It's not one thing, it's the other thing, right? Oh, I see. This is 0, because now it's sine, so you plug 0 in for sine, sine is 0. All right, so very good. So C2 is just going to be 20/16. C2 is 20/16. Simplify that, divide top and bottom by 4, that'd be 5/4. Finally, the solution, x of t for motion in this scenario is going to be 5/16 e to the negative 4t plus 5/4 t e to the negative 4t minus 5/16 cosine of 4t. Great. Let's make sure that's right. Yeah. Okay, so yeah. A lot of easy places to make mistakes. Speaking of making mistakes, let's look at number 14 and try to run through this one. So number 14 is the driven undamped motion. So mass is given in the European units, the kilograms. So mass is automatically just 2. The spring constant is automatically given as 32 Newton meters. And so it comes to rest in the equilibrium position, starting at t equals 0, force is applied. We'll find the equation of motion in the absence of damping. So again, the initial condition 0, 0, x prime of 0 equals 0. Let's get our information. We need omega squared basically, which is k over m. So in this case, it's easy, it's just 16. So our differential, let's get the differential equation first, right? So it's x double prime plus 16 x equals the driving force, which this time is 40 e to negative 4t, but be careful, you gotta divide it by m. So it's really 20 e to negative 4t cosine of 4t. Okay, so get the associated homogeneous version solved. So its characteristic equation, of course, m squared plus 16 is 0. So m will be plus or minus 4i. So the complementary part of the solution is going to be c1 cosine 4t plus c2 sine of 4t. Now build the sort of, with the annihilators, build the associated sort of auxiliary equations. So the first annihilator, just what we already have, the d squared plus 16. And then to annihilate this junk, I need to have roots of m equaling negative 4 plus or minus 4I, right? So you could write, FOIL it out and kind of figure out what your values are. But I'm just going to write d minus negative 4 plus 4I, and then d plus negative 4, d minus negative 4 minus 4I. So d minus negative 4 minus 4I. Okay. Generally speaking, when you don't have repeated answers from the homogeneous and then from the annihilating stuff, the extra annihilating stuff, if there's not anything common to those, you're probably not going to have to worry too much about what your particular solution will look like. It's just going to be what you think it is. But anyways, the roots then will be negative 4 plus or minus 4I, and then plus minus 4I. So the solution to that differential equation would be y equals all the c1 cosine 4t plus c2 sine 4t, which we already know is the complementary part, and then the rest will be the particular, right? So for the particular, it's going to be plus e to the negative 4t times c1 cosine 4t plus c2 sine 4t. And you're reading the book, they don't go through this process over, they just kind of skip over it because they assume that you can handle this on your own now. I mean, the book teaches two ways of doing this method. The other way they teach it is less kind of programmable. They kind of just tell you if the right-hand side looks like this, then your solution will look like this, etc. Anyways, we can get our particular solution here then, because this is the complementary part up front. The rest is the particular. So we'll have e to the negative 4t times a cosine 4t plus b sine 4t. And of course, this one's going to be a nightmare to get to the second derivative, but let's do it. So I'll end up with like 8 terms in the second derivative, which would be quite annoying. Anyways, these should all be x's. I'm just writing y's. I don't mean to. They should all be x, 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 and then x here. Okay. Alrighty then. So let's get the first derivative. I need to go to the second derivative though eventually. I'll take the derivative e to the negative 4t first. So negative 4e to the negative 4t times this stuff. Then leave e to the negative 4t alone and take the derivative of the a cosine 4t plus b sine 4t. Then get the derivative of that. So now there's going to be 8 terms. First, I'll take the derivative of this. Leave this alone. Then I'll take the derivative of this while leaving this alone. And now I'll take the derivative of this and leave the other part alone. Leaving that alone, and now I'll take the derivative of this, but leave that alone. So that will be negative 16a cosine of 4t minus 16b sine of 4t. Okay. Alrighty then. I don't really need the middle stuff. What I need then for my differential equation, I need 1 x double prime and then 16 x's, right? So looking at this stuff, I need 16 of these, and then just, I guess, 1 of these. All right, I'm going to try to do some, cancellation if possible. And I can kind of see that 16 of these are going to cancel out with all of these guys here, right? Because there's going to be negative 16 of the same thing. Okay, so I get that cancellation at least. So it was 16, right? Omega squared is 16. And then I'm just kind of left with all this other stuff. Maybe I can do a little bit of cancellation there. I'm not even sure. Okay, we'll see how it goes. So what's left over then is the 16 e to negative 4t times a cosine 4t. Let's see if I can combine some of this, right? So if I distribute this thing, I'll get positive 16a sine 4. So there's going to be some common ground between those two and these two, right? So you have 16a the sine t and 16a the sine t there. Let's get the first parts, this stuff written first. 16e to negative 4t, a cosine 4t plus 16e to negative 4t, b sine of 4t. Then there's going to be plus 16 of these, and 16 of these is 32 e to the negative 4t, a sine of 4t. And then there's going to be negative 16 of those, and negative 16 of those, so that would be minus 32 e to the negative 4t, b cosine of 4t, all equaling that 20 e to the negative 4t cosine 4t. Then let's see if there's anything we can combine together. So not really. All right, so I'll have then equating the cosine functions together. So there's one here, there's another one here, and that should equal the coefficient on that thing there. So you have 16a minus 32b equals 20. And then this thing and this thing should equate to the coefficient on the right. There's no, e to the negative 4t, e to the negative 4t sine 4t on the right, so that's just 0 on the right. So we have 16b plus 32a equals 0, hopefully. So I could solve at least for one of the variables. 16b equals negative 32a. In other words, b equals negative 2a. Plugging that into the other formula, then 16a minus 32 times negative 2a equals 20. So I'm getting 16a plus 64a's equals 20. So that's going to be 60, 70, 80, a equals 20, so a would equal 1 over 4, and so b is equal to negative 1/2. Okay. Let's make sure I get my a's and b's right. A is with cosine, b is with sine, and then my complementary part. Okay, so x sub the solution again is the complementary part, which is c1 cosine 4t plus c2 sine 4t plus the particular part, which will be plus 1/4, and again a I think goes with cosine, yeah, 1/4 e to the negative 4t cosine of 4t minus 1/2 e to negative 4t sine 4t, and then you're kind of stuck with trying to figure out those constants, right? The constants on the cosine and sine. You got to go back to your initial conditions then. So x of 0 and x prime of 0 is 0. I'm going to need to get the derivative of this thing. And again, that will be a nasty little critter with 6 terms in it. So the derivative x prime is going to be negative 4c1 sine 4t plus 4c2 cosine 4t minus e to the negative 4t cosine 4t minus e to the negative 4t sine 4t plus 2e to the negative 4t sine 4t minus 2e to the negative 4t cosine 4t. Okay. Plugging 0, 0 in the first guy, I get 0 is c1 plus 1/4. So that implies c1 is negative 1/4. Let's see if I'm on the right track. Yeah. And then plug in 0, 0 on the other guy. 0 is negative, well, just 4. And then minus, that will just be 1. And then minus 2. So 4 minus 1 is 3, minus 2 is just 1. There's no way that's right. Yeah. So I must have lost something somewhere. It's oh, sorry, it's 4c2. So I can't. All right, so 0 is 4c2 minus 3. Yeah, that'll work. And then 4c2 is equal to 3, and then c2 is equal to 3/4. So our final solution then, x of t is going to be c1, which is negative 1/4 cosine of 4t, plus c2, which I think was just 3/4 sine 4t, plus 1/4 e to negative 4t cosine of 4t, minus 1/2 e to negative 4t sine 4t. Okay, let's make sure that's right. Negative 1/4 cosine, 3/4 sine, 1/4 e cosine, negative 1/2 e sine. Okay, so there it is. All right, so sorry that this video is a little long. Some of these problems are quite annoying, but I just wanted to have them there for reference. As usual, thank you for watching, and I'll see you next time.